Hi there. Today we'll look at TransGAN, Two Transformers Can Make One Strong GAN by Yifan Qiang, Shiyu Cheng, and Changyang Wang. So in this paper, the authors attempt to make a generative adversarial network, a GAN, out of only transformers. So far, attention or transformer-like things have been used in GANs, but they've always had some component of convolutions in there. This paper attempts to do generator and discriminator just using transformers. They discuss what is needed to do that, how they built the architecture, and there are a couple of training tricks that make this work and actually make this competitive to current state-of-the-art architectures. So the biggest data set they tackle is CelebA, which is 64 by 64 pixels. But, due to their numbers suggest you can scale this much larger. The model is called TransGAN. I don't know if this is a bit of an unfortunate naming. I guess the question is, which bathroom do the TransGAN go to? I don't know. In any case, let's dive into the paper. Let's check it out. If you like content like this, share it out, leave a like, and tell me what you think in the comments. So the paper is fairly straightforward. Actually, there is code available, so definitely check that out. I'll link that, of course, in the description. The paper is fairly straightforward and answers one question. Can we build a strong GAN completely free of convolutions? So usually in GANs you have convolutions both in the generator and the discriminator, and their goal is to just replace that using transformers. As we say, their contributions, there are three. The model architecture. So the discriminator, as we're going to see, is a vision transformer like we saw before. The generator is also a transformer that is interlaced with upsampling. Then training technique, they do discuss that you do need three things specifically. So you do need data augmentation, you need multitask code training for the generator, and you need a localized initialization for the self-attention in order to make this work. And then they reach a GAN. So their biggest model, TransGAN XL, reaches very competitive FID scores and also very competitive inception scores. Wait, this is here is the inception score. The IS score is a bit of a misnomer too. I mean, the S is already score, but it's okay. Yeah. So first, architecture. The architecture is fairly straightforward. So for a GAN, you need a discriminator and a generator. Now the discriminator, as I already said here, that is the exact model from VIT, and I've done video about it. The paper is called A Picture is Worth 16 by 16 Pixels or something like this. Well, I don't exactly remember, but you can check. You can definitely find that. It is a transformer-based image classifier. So what you do with an image, so here you see an example image, this image of the dog. What you would see if you were to feed this into the discriminator, of course the discriminator gets the output from the generator, but also the real data. You would unroll that picture into these kind of sub-pixels, as you can see right here. But not into full pixels, but into kind of these super pixels. So every one of those super pixels will then be unrolled. This is this flattening operation right here into a single vector. And that then is like a word in a sentence. Okay, so this picture here just becomes a series of vectors. And then you can simply apply your regular transformer architecture. So every patch becomes a vector, like a word embedding, and then you just go ahead and you put a transformer encoder. So this is very much like BERT, for example. It is a similar architecture. As you say, you can go look at this paper. And at the end, you simply classify whether it's real or fake. You do have to add position encodings because, lacking the convolutions, the transformer has no idea where in the picture a given thing appears, because it is not a sequential architecture, it's actually a set transformation architecture. So you do need to add positional encodings, but in general, this has been shown to work quite well in things like ImageNet classification. On the generator side, it is very similar, but a little bit different. So here, what you need to achieve are, of course, are these 32 by 32 by 3 pixel image, right? That's at the end. You need to achieve that. Now, you can't just go the reverse from over here and somehow try to predict these patches, because that, I guess that is just too, if you predict these patches as such, like independent patches from each other, the borders would never match up. In a discriminator, this does not matter, because you don't need to construct the image, you simply need to classify it. But if you need to generate images, it doesn't look good if you have these borders here where things don't match up. So you will actually need to produce an image that is in the size that you require. So in this case, 32 by 32, and of course 3 color channels. So the way they achieve it is by this upsampling architecture. The problem with transformers, of course, is they do require quite a bit of memory and also compute, because the attention mechanism basically connects every single token with every single other token in each transformation. In this case, they connect every pixel to every other pixel. Now, if you were to do this for many, many layers, that is going to be 32 squared in this case, memory requirements. Pretty quickly, you will run into problems. So what they do is they have intrinsic upscaling of their dimensions. What does that mean? So at the beginning, you have like some noise input, and you have a little MLP generating the initial sequence. Now, the initial sequence is going to be 8 by 8 by number of channels. You can see there are also position encodings right here. So your noise generator essentially creates an 8 by 8 grid. Okay. Let's say, for the sake of argument, we create a 2 by 2 grid instead of an 8 by 8 with a number of channels. So here is the number of channels to the back. You want to unroll those into 4 vectors of these channels. 1, 2, 3, 4. You get the idea. And then that you feed into the transformer. So now you have 4 tokens, or here 64 tokens in that case, but in our case, 4 tokens that you feed to the transformer. So right now, at this stage, this is like a sentence with 4 different words. So you run that through M layers of the transformer. And then at some point, you decide, okay, now it's time to do upscaling. And in the upscaling, you take those 4 words. So you take that 2 by 2 image that you have right here with the C channels, and you generate somehow from it, and we're going to look at, I'm going to draw this over here. So you generate somehow an image that is double the density in pixels. So this is now a 4 by 4 image, but it has less channels. So the way they save memory is that they start out with many channels, but very coarse resolution, and progressively as they go up the layers, they upsample so that they have more resolution but less channels. Okay, and so this is very much like the convolutional GANs do. So like they would start out with a very coarse image grid, and then they do some kind of upsampling, some kind of strided pooling, and so on, in order to reach higher pixel densities. And with the higher pixel densities, they often decrease the number of channels. So you get a trade-off between the density and the kind of depth of information. At the end, they end up with their target resolution and a number of channels, and then they feed that through they feed each individually through a small linear projection in order to project that to the 3 channels. So that's how they end up with 3 channels. So how exactly does this upsampling work? By the way, I hope you can see the whole pipeline now, right? You start out by this is sort of noise generated. This is what is derived from the noise, and then the input is just transformed, upsampled, transformed some more, upsampled, transformed some more, until it is at the target resolution. Thereby, in the lower layers, you have lots of information depth, not much resolution. In the higher layer, you have lots of resolution, but not that much information depth anymore. So the computations higher up might be more localized. They might be more to do with the exact kind of the exact details of that particular patch in the image, right? All of these things are representative of patches, especially in the downscaled. Like this pixel right here is representative of all the pixels that are going to be generated out of it. So of this one layer higher, and of course even one layer higher is going to be of its own 4x4 pixel grid. So the computation you do down here on this pixel will affect all of these pixels later. The way they do the upsampling is by this PixelShuffle algorithm that they have from this paper right here. And I'll link to that, of course, as well. So this is a paper that was, as I understand it, originally derived for convolutions, and it asked how can we do sort of convolutional operation on high-resolution images without having to do the compute for high-resolution images. And they figured out that if they had a high-resolution image, they can sort of they can rearrange a high-resolution image into a smaller resolution image with more channels. So here you see you have, they call this R squared, number of channels. So this number here is R squared. And they can sort of unroll this image into this one. And they do that by treating these things here. Maybe you can see this is a repeating pattern as sort of superpixels. You can see that. So one of these superpixels is going to be one column here. All right, so this way, so you're going to upsample by having lots of channels here, doing the computation on as if they were lots of channel in a low resolution image, and then you upsample by just unrolling the channels locally. So by treating each of these things as just, one superpixel with the elements of the channels being the, kind of the different pixels in the neighborhood. So you want to unroll that, and then after that you continue with your processing, with putting this through the next layers until you upsample it again by unrolling some more channels. I hope that's clear. So you're going to start out with a lot of channels, because each time you unroll, you're going to lose some of them. You're going to trade off some of the channels, channel depth, for more resolution. All right, so here you can see every time they upsample their resolution by 2, they need to divide the channels by 4, because you need to upsample by 2 in the width and in the height direction. Actually, it's not even necessary. You can totally choose this, because in the attention block, as you can see here, in the transformer block, you have this part which is the attention mechanism. And then you also have this part right here, especially this MLP here. It takes in each token of these. It takes that after it goes through the attention, after the whole thing goes through the attention. Each of the tokens is fed separately through the MLP. So the MLP, it's actually not necessary that the output dimension of the MLP is the same as the input dimension, except for this skip connection right here. Now, if this skip connection, like in ResNet, had some sort of a linear projection as well, then you could totally think of changing the dimensions here. Though I'm not even I'm not even sure. If you do the projection, isn't this just the same as the MLP with if you feed each individually? Maybe there's no point in having the skip connection at all. In any case, you could probably get around that, that requirement to have this exact number of channels. Nevertheless, that's what they do. So the generator is actually manageable memory-wise because it does this trade-off as it progresses up. It generates an actual grid in the resolution of the image with the required channels being a projection of the final channels here out of the transformer. Then it's fed into the discriminator. The discriminator immediately divides the image into patches, interprets each as sort of a token embedding, and then simply it adds positional encodings and then simply uses a transformer like BERT, and at the end you have this CLS token like you have in BERT, and that classifies real or fake. You can backprop through the whole architecture, and that's a GAN for you. So that was the architecture part. And now, so they do a lot of good ablations where they say, okay, so we have a generator and the discriminator. What if we have kind of this auto GAN is one of the things they compare with. So what if we do that? And then what if we just replace the generator with the transformer? What if we just replace the discriminator? So they find out that they can replace the generator just fine. And that even gives competitive performance as soon as they, transfer the discriminator to a transformer. That drops in performance. So in order to really make this work, they need some more tricks. They have 3 tricks. The first trick is data augmentation. They say data augmentation is crucial for TransGAN. And the type of data augmentation they do is also from a paper for data augmentation for GANs. It's this right here, differentiable augmentation for data efficient training. So the whole point is that your data augmentation, so the augmentation T right here, is a differentiable function. So data augmentation is things like cropping or changing the brightness, color jitter, rotating, and so on. So as long as that's a differentiable operation, you can use this technique right here, where you backprop through the augmentation. You can see right here in the generator update, you actually backprop. So the backpropagation happens through the T function, and therefore you get a much better signal. Plus, you get all the benefits of data augmentation. And the point they make in the TransGAN paper here is that given that transformers don't have this convolution, they don't have this locality bias built into their architecture, they need a lot more data. And we know that transformers, they work well if you have an abundant amount of data, and you can sort of get around having lots of data a little bit by using data augmentation. So they argue that data augmentation, it works for all GANs, but it helps a lot more in these transformer-based GANs because the transformers benefit better from having lots of data. Again, the story about transformers is pretty clear. I think if you have lots of data, they tend to work well because they're just a more general architecture. So here you can see in the different GANs, you can see that the augmentation, which is when the check mark here is, it helps sometimes. You can see not always. Sometimes here it does fairly well, but here in the TransGAN, you can see that adding data augmentation drastically improves the results and already gets these GANs into the ballpark of the state of the art. Not yet there. There's still a big difference, but it gets them in like target distance. So the second trick they have is this co-training with the self-supervised auxiliary task, and specifically they do super resolution. So where am I going to write this? So this here, it's a super resolution task, right? Super resolution. And what they mean by this is simply they, in addition to the whole GAN training, right? So here you have the data set, I know, beautiful. So the discriminator over here, the D, it gets images from the GAN, as you can see right here, and it also gets images from the dataset, right? And that's your main GAN loss. So here you have the discriminator loss, you backpropagate that through the GAN, you update all the parameters. What you also do is you take dataset images, you put them here as a target. So this is the target for the GAN. So the GAN needs to output something. And what does it get as an input? It gets this thing, but scaled down. So how am I going to say this? Big picture goes to small picture. Okay. So you take pictures from your dataset and you deliberately downsample them. You deliberately you might even add some noise or something, but I guess they simply do lower resolution. So LR means low resolution. And then the task of the GAN is from the low resolution input, predict. Like it needs to predict the high resolution image. It's completely different pipeline than usually, because it actually gets the small thing, the small real image as an input. The generator usually never sees real data, right? Now it gets a small resolution. This is not the same image that goes to the discriminator, by the way, I think at least. This is just a different thing you can also do. You mix into your batches of noise GAN samples with this loss. You simply also mix things. You mix this loss right here, the super resolution loss. So you have this loss, and then you have the loss from the super resolution, and you simply add them with a parameter to trade off one or the other. And this helps the generator to, so given a low resolution image, these stages here will have to learn to sort of upsample realistic looking images from lower resolution images. And that's what you sort of expect this GAN to do. So it makes sense that this is a good auxiliary task. And this turns out to help quite a bit. So as you can see right here they have it with data augmentation. And if you add this task here, the scores improve again by a bit. And then the last trick they have is to also do this locality-aware initialization for self-attention. And you can see that again pushes the scores. So what is this last trick? In this last trick, they say, look, the convolution, it seems to be a pretty good prior for images after all, right? That's why CNNs are so effective. It seems to be a good prior to look locally, like to have local features. But of course, the transformers, they are more powerful. And eventually, they want to look at the whole picture. But maybe it makes sense to first teach them that local things matter. And once they're at a certain quality level, we can kind of let them look at other pixels in the image. So what they do is they handcraft a schedule. And so over the course of training, have this gradually increasing receptive field. So in early training, they simply say, you're only allowed to look at your immediate neighborhood. So each superpixel right here, remember this is in a downscaled world sometimes in the generator, you're only allowed to look at the immediate neighbors. So we introduce a mask, that says it here, by which each query is only allowed to interact with its local neighbors that are not masked. Okay? And then say, different from previous methods during training, we gradually reduce the mask until diminishing it. Eventually, self-attention is fully global. Okay? So at first, they say, in the transformer layer, you have the keys down here. So you have a series of keys, and you have a series of queries from the individual tokens. And they say for a particular token, you're only allowed to look at your immediate neighbors as if you aggregate information. And then later they say, okay, now training, so this, only look at this, and you can only look at your immediate neighbors, and so on. And later in training, they say, okay, now you've sort of learned well. You're now allowed to also gather information from kind of further out, until at the end of training, all the queries are allowed to look at all the keys. I'm sure that if you engineer this smartly, this is local attention, right? This is known as local attention. And you can also make a bunch of, speed ups probably in early training here. You can see right here in early stage, only immediate neighbors. In middle stage, they sort of widen the circle of where you're allowed to look. And in the final stage, each query is actually allowed to do the full attention. So when I saw this, I was like, okay, here I'm told we're going to build a GAN absolutely without convolutions. All we're going to replace with is kind of a linear operation that is applied over the whole image in a fashion that it only gets to look at its neighbors, right? It's totally not a convolution. It's just a linear operation that is applied equally across the image while only looking at your immediate neighbors. I'm so glad we're building GANs without convolutions. Convolutions are for losers. We're all for locally applied linear transformations over the whole image that only can look at their immediate neighbors. So yeah, no, I mean, you get the point. This is essentially an attentionized version of a convolution, but with training, as training progresses, they do release that constraint. This is simply to help the GAN do training. Though I am fairly convinced you wouldn't maybe have to do this as a fixed schedule, right? This is like a fixed schedule. I say, okay, you're allowed to look at this many neighbors, and then after this many steps, this, and so on. I'm fairly convinced you could somehow formulate this maybe as a 2-player game, right? But like another GAN thing, or maybe another GAN thing, or sort of a self-play thing where the one player tries to sort of get the most information out of the neighborhood, and the other player tries to sort of constrain that player, but it only has a certain amount of budget and so on. I'm not sure. I mean, but you could probably do something smarter than simply a fixed schedule that is adaptive to the difficulty of the task. And you would also in turn lose a bunch of hyperparameters that you need to build this schedule over here. All right. The last thing they do after all the tricks is, of course, what everyone does best with transformers, and that's just scaling that thing up to many layers, many dimensionalities, and I don't know if they do a lot more data. Probably not in this case, but if you had more data, it would also work better. And thereby, they do reach scores that are state-of-the-art, or at least very competitive with state-of-the-art. So their TransGAN XL model, as you can see here, for example, on CFAR10, they do reach very competitive scores, beaten only by StyleGAN V2. They also reach very good or state-of-the-art scores on other datasets. Here on STL10, they are the best. Yeah. So there is it's cool. By the way, it's nice to see papers going back to kind of the 64 by 64 images, because we're so used to these super duper high resolution GANs now. This reminds me of old times. Yeah. So the paper as a whole is pretty cool. It's actually pretty straightforward. As I said, they develop an architecture that works, that is actually computable with this kind of upsampling and the PixelShuffle channel reduction as they go along. The VIT discriminator, then they present 3 tricks to make that work. It's data augmentation, it's super resolution task as a code training task, and it's this localized locality-aware initialization for the attention, with the decreasing with the schedule over training. And finally, they scale that model up, and that gives them pretty well performing GAN. And it's only made of So it has no convolutions. Their goal isn't to use only transformers. Their goal is actually to use no convolutions. Yeah, that was it for me. Tell me what you think in the comments, and I invite you to check out the paper and the code. Bye-bye.